Good afternoon, everyone. I am Raphael, Toledo, a doctoral student at University College London, and I'm going to present to you a work by George Danesis, Jan Goldberg, and myself, Lower Cost Epsilon Private Information Retrieval. So, as you may know, private information retrieval, or PIR, is actually a subject which has been quite thoroughly studied, but it still suffers from scalability and cost issues. So we worked on it for a very precise context I'm going to tell you just now. So there is a project called Certificate Transparency, which tries to fix a structural flaw of TLS certificates. In order to fix TLS certificates, mistakenly published certificates or compromised ones, all the TLS certificates must be published on the public ledger. So actually this is really good, it's a fix, but it's also a privacy breach. If I want to go on any website to look at cats, for instance, I will have to contact the ledger, as you can see on the right, and ask on the log if there is a certificate corresponding to this website. An adversary looking at my communications or owning the log will be able to see what website I intend to access. So of course, for cats, it's not really important, but it can be really sensitive informations. As you can see, in middle 2014, about 5 million certificates were published. So we are talking about another scale for PIR. Actually, there is another project which began quite recently called Let's Encrypt, which tries to help people creating and managing certificates. Since 2015, about 4 million certificates were published, and as you can see, the growth is exponential. So what does it mean? It means quite simply that in the ledgers, there are going to be tens of millions of certificates eventually, and we'll have to give privacy to users with these tens of millions of certificates. Actually, there's a solution for that, which is PIR, but PIR doesn't scale. PIR only requires sublinear communication costs, but doesn't require anything for computation costs. It can be linear, it can be actually a little more, it's not a problem. IT-PIR is a PIR family where the databases are replicated, and the users have to contact all of the databases so that the adversary has a partial view of the system. Having this partial view of the system, some privacy can be achieved. The costs are though linear in the number of databases, but also in records. So if you remember what I just said about CT, Certificate Transparency, since it will be a global solution, we'll have hundreds of databases all over the world, and we'll have tens of millions of certificates. This is a huge problem. So what we're trying to do now is make PIR a bit more scalable so that we can have some privacy when we are looking at cats on the internet. What's the threat model? So the threat model is pretty simple. I am an adversary, and I'm going to give to a user 2 requests. The user will pick one of the 2 and will require the databases with IT-PIR. We consider that all the databases except at least one are compromised. They will be curious but honest, so they will process all the requests as normally, but they will give information to the adversary. And we also assume that public key encryption is done so that nothing in the communication can actually be guessed. In order to look at the information leakage in this game theory scenario, we actually use differential privacy. So this is actually pretty simple. The adversary will just look at the information he has and will try to look what is the most likely request which have been queried. So what we want to do as researchers is just bound the difference between the likeliness of a query being a record being queried or another, given a certain observation. This definition has actually to be a bit strengthened. It's not for a specific observation, but for all sets of observations. So what does it mean, actually? I will take a very bad example, and this is not computational PIR. There are 2 cases. I'm a target, and I'm directly contacting the database. So I'm sending a request for the website I want, for the certificate I want, with many others. This is actually really bad. The other case, it could be considered slightly better, but actually they could be considered as equivalent. The target user uses an anonymity system such as Tor to access the database and access the records. In that case, in the single database scenario, as the adversary can see everything, all the computation done on the server, it can see which record has been queried or accessed or not, So he will be able to say, you have queried a record among those ones, and the privacy you have is consequently null. What we try to do is actually do IT-PIR, so we consider several databases. And what we can show is just using several databases, with the assumption that at least one is clear, is innocent, we can achieve some privacy. However, as you can see in the table, the privacy we have is really bad. So if I want a good privacy, we can say that we want epsilon lower at 0.01, and the adversary has a certain number of databases, 10%, 50%, 90%, or all but one. We can see that actually the user will have to query nearly all of the database, all the records, to achieve good privacy. This is not good. So what we have looked at is actually another variant of traditional core PIR, which is quite simple. We represent the records and the databases in a matrix. The user will actually ask the records he wants in an odd number of times, and the records he doesn't in an even number of times. The request will be actually the rows of the matrix. Each database will actually compute the XOR of the answer blocks. The user will receive actually as many blocks as there are databases. It will recombine all the blocks on its side, and he will retrieve the blocks he wanted. We actually achieve way better results. However, here the number you see is not the percentage of records that the user access. It's a percentage of records the user access per database. If you want perfect privacy, this percentage must be 50%. So 50% is actually normal PIR. What we want to do is cheaper PIR. And what we see is that if we have the strongest adversary possible and we want pretty good privacy, we nearly need to contact 50% of the records. So this system is also not good enough. So that's why we introduce actually an anonymity system between the user and the databases, so that each user can actually contribute in the overall privacy. So we got a composition lemma, which states that the participation of user give a certain privacy. You can see in red in the tables, the new privacy level achieved when using the anonymity systems, U being the number of user and epsilon being the previous privacy. In the red cases, you can see actually that the privacy level is lower because epsilon is higher. This is due to the lack of tightness of the bonds in the composition lemma. What is interesting to look at is actually the asymptotic results. So for instance, if I were to look for an epsilon of 1 and 1,000 users, I would see that the new epsilon would be actually good. It would be 10 to the power minus 2. So here you can see the results we have of direct requests using the dummies and sparse PIR, the weaker variant of core, and the composition of them with the anonymity systems at the bottom. You can see that we can achieve better privacy and these pictures are for 100 databases and 1,000 users. So I talked about introducing differential privacy in PIR, introducing anonymity systems to enhance the privacy of people, and we analyzed weaker IT PIR designs to make them arbitrarily good. So thanks a lot, and if you have questions, please feel free.